the cloud. Okay. Good. All done. So, Ben, I give you the floor and to introduce Cora Dvorkin, that we have the pleasure to welcome today.
Thank you.
This meeting and colloquium. So I give you the floor, Ben.
Thank you. So it's a great pleasure to be able to welcome Cora, Cora Dvorkin, I should say Professor Cora Dvorkin from Harvard for the Institute seminar here at IAP. Remotely, we're taking advantage of people being used to remote meetings. And to have her from her office, I expect in Boston, Cambridge. And so Cora did her undergraduate studies at Buenos Aires, and then her PhD at the University of Chicago, and then went on to do her postdoctoral work, first at the Institute for Advanced Studies in Princeton, and then at an Einstein Fellow and a Fellow of the Institute for Theory and Computation at Harvard, from where she then continued as was nominated to be went on to the faculty at Harvard, where she was awarded in 2018 the Scientist of the Year Award from at Harvard, and has recently been awarded a Department of Energy Early Career Award, amongst many other recognitions and fellowships that she has been offered. So Cora's work, of course, spans particle astrophysics, questions about the beginning of the universe, particle astrophysics questions as they relate to cosmology. And she has recently become more interested in questions around using machine learning, and made contributions there in terms of applying machine learning to cosmology and astrophysics, also as part of the new center at Harvard and MIT and neighboring institutions. So today she will tell us about unlocking new physics out of astrophysical data sets. Take it away, Cora.
Thank you very much. Do you hear me well?
Very well, thank you.
Perfect.
Great. So thank you very much for the invitation and the kind introduction. And I hope everyone is doing well in these still difficult times that we are living. And yeah, I'm happy to see many familiar faces here, and I hope I will be able to see the non-pixelated version of yourself soon. So today I will tell you about some of our efforts with my research group to unlock new physics out of astrophysical data sets, both from large and small scales. Whoops. There. So here's where we stand in cosmology today. We have a standard model of cosmology known as lambda CDM. And this model has been extremely successful on cosmological scales among a wide array of different observables, from the cosmic microwave background fluctuations to the clustering of matter and measurements of the expansion history of the universe. So here in this plot, I'm showing you the matter power spectrum as a function of wave number. And you can see that this is a log-log plot, and it covers 4 orders of magnitude on each of these axes. The black line here shows the predictions of our lambda CDM standard model. And each of these data points that you can see here is a measurement interpreted within the context of this model as a measurement of the power spectrum. So what's interesting about this figure is that it's spanning 14 billion years of history of the universe. It's spanning 4 orders of magnitude in length scale and a wide variety of cosmological observables. And we can see how the lambda CDM model fits them all beautifully. But of course, we still have fundamental questions that remain unanswered. What is the source of the accelerated expansion of the universe? What is the physics that seeded the first structures in the universe? What is the nature of dark matter? And this last question is the one I will focus on today. So what do we know about dark matter? Well, we know that it doesn't emit or absorb light in any significant degree, so you might as well call it transparent matter, but it does have mass, and hence it exerts gravity on visible particles. And this is how we know literally everything else about dark matter. We have learned from cosmological observations that it is about 84% of all the matter in the universe. We believe that it is all around us and that it forms the scaffolding for the visible universe. But there are no really good candidates in the standard model, so we still have open questions. What is it made of? Does it interact with ordinary particles? If so, what are those interactions? So let me illustrate here our relative ignorance by focusing on just one parameter, the mass here. It turns out that it could range over 90 orders of magnitude, going from very light masses, for example, axions, to the famous WIMP, to compact objects. And this is a huge range. A related question that we could ask is, could there be new light relics produced in the early universe beyond the standard model? And if so, how can we measure them? So the plan for this talk will be to walk you through our efforts with my research group to unveil the nature of the dark sector, both at large and small scales. That's how I divided my talk. And I will start from the smaller scales. So as I was mentioning just now, in the past few decades, we have measured the large-scale structure of the universe very accurately with many different probes. And this has allowed us to put precision level limits on different kinds of dark matter scenarios. On smaller scales, however, there is a lot of structure, but it is not as well understood. And furthermore, many dark matter models that agree at large scales, mainly by construction, show differences at small scales. So observations at small scales provide fertile grounds for testing different dark matter scenarios. As an example of the effect of different dark matter models on subgalactic scales, I'm showing here two different projected dark matter densities coming from high resolution embodied simulations. One over here coming from a simulation in a CDM scenario. And on the right here, I'm showing you a simulation with some exotic dark matter microphysics that results in dark matter clumps that are more susceptible to tidal stripping. So you can already see by eye here that there is a lot more structure in the CDM model than there is in this exotic dark matter scenario. And this is just one example to illustrate the fact that new dark matter physics can lead to interesting phenomenology that is observably different from CDM on these scales. So the idea that I will tell you about is to probe the distribution of dark matter on small scales, and by this I mean kiloparsec scales, to falsify or corroborate the cold dark matter paradigm. So our tool for this will be strong gravitational lensing. So let me give you here a one slide review of gravitational lensing. Basically, we will have a background source at some high redshift, which will be a galaxy in our case. And there will be a foreground galaxy between us here in the telescopes and the source that deflects the light because of its gravitational field. So from our perspective, we will see extended arcs. And the idea will be to use these images to see if the lensing galaxy here is clumpy or smooth. So the idea that has been suggested about 20 years ago by Mao and Schneider is that substructure in the halos of galaxies will locally perturb lens images. So by looking at the residual between the image predicted by modeling the lens galaxy as a smooth mass and what is actually observed, we can infer the presence of subhalos. And the advantage relative to other methods for detecting dark matter is that we do not need to assume a specific coupling between the standard model and the dark sector, in contrast to direct detection experiments or colliders or other indirect detection experiments. And so in this sense, I like to say that we are model independent. Furthermore, the lowest mass subhalos are largely devoid of stars. So detecting them with a gravitational technique is the only possibility, since these subhalos cannot be seen directly. So with my group, we have done work in this arena following two different and complementary approaches. The first approach is what I call a direct detection approach, where our goal is to resolve individual, more massive perturbers, and from there infer their properties. The second approach is a statistical detection approach, where we want to marginalize over individual subhalo properties to learn about the subhalo population characteristics. Here, basically, we are exploiting the steepness of the subhalo mass function, the expectation that we have a huge population of these very low mass subhalos to try to statistically detect their collective perturbation on images. So I will start with the direct detection approach, which is the most intuitive one. And once we understood this approach, we will go to the statistical one. So we will have the same picture as before, but now we will add a subhalo or more than one in the halo of the lens galaxy, and we will look for a small deflection as the light from the source crosses the lens. One of the main methods used for direct detection of subhalos is known as gravitational imaging. Much like what Mao and Schneider proposed, the underlying principle is that if you have some dark matter clump lying close to an imaging projection, there might be some visible distortion that you can try to reconstruct. This figure over here that I took from a paper by Simona Veghetti and collaborators very nicely illustrate the pipeline that goes behind this. So basically we start from the data, a strong lens galaxy, and we have to model the smooth component of the object doing the lensing, assuming that there are no dark matter clumps. And we also need to reconstruct the source. And once we have these two ingredients, we can obtain the smooth model image. And basically by trying to minimize the residual between the data and the model, we can ultimately reconstruct the surface mass density over here that gave rise to the original data set. In this particular case, we can see the reconstructed surface mass density or the convergence field. And we can see that it has an overdensity over here. And this was a 10 to 12 sigma claim detection of a dark matter clump at this position in the image. So far, using this method, there have been 3 detections of subhalos in the order of 10 to the 8 to 10 to the 9 solar masses from about 30 images analyzed. What I want to emphasize here is that this is a very computationally expensive process, and it can take up to months to analyze a single system. So if you have tens of images to analyze, that's okay. But in the next few years, we expect tens of thousands of these lenses to become available for this type of science through, for example, the Vera-Rubin Observatory and other experiments, in addition, of course, to further follow-ups by the Hubble Space Telescope and the ELT, among others. And in fact, there are already many recently discovered by the Dark Energy Survey that are waiting for follow-ups. And this is great, since this vast increase in sample sizes will provide a leap in our understanding of dark matter. But obviously, it is unsustainable to take months to analyze each system.
Can I ask
So,
a question, please?
yes.
Sorry. Hello. Yes, so you just mentioned that it's taking a lot of time to analyze these images. Could you give us a flavor of why it's taking so long? Yeah,
so I can tell you by personal experience, there are a lot of, so first of all, well, you have to run, first of all, there are many choices that you can make for the lights, for the lens light subtraction, for the source reconstruction, for the profile that you consider. And you have to run, in general, these likelihoods have many local maxima. So you have to run nested sampling algorithms to search for the right one. And, that's the basic reason why it takes a lot of time, because there are many choices that you can make. And you have to make sure that after running the MCMC samplers or the nested sampling, you have to make sure that what you're actually reporting is the true true maximum of the likelihood.
So still a little bit experimental is what you mean. It's a mix of computational time and also a bit of smelling what would be the right models and.
Yep, definitely. And many times, yes. So they are just sometimes different profiles give you different answers. Different landslide subtraction give you different answers. So you have to do consistency checks. Yes. What I was saying, yes. So basically, it is. I was saying that it is unsustainable to take months to analyze each system. So what motivated us, together with my former PhD student Ana Díaz Rivero, was the following question: can we automate a procedure like direct detection using machine learning, making this process much faster? And if we understood the sensitivity of our machine learning model well enough, we could still combine detections and non-detections to probe different dark matter scenarios. So what we did is we turned the problem into a binary classification task. Basically, we asked the question, for what subhalo masses is the network able to recognize the lens as having subhalos versus not having any? And in this way, we could identify promising candidates. And since most images analyzed with gravitational imaging yield non-detections, this could cut down analysis time and resources by a large factor. And so in this first work, using a very simple architecture, a convolutional neural network, we found for realistic levels of HST noise that we could be sensitive to subhalos with masses around a few times 10 to the 9 solar masses, comparable to the numbers cited in the literature for real detections, even in the presence of correlated noise. We also tested for that. And we found this result very promising, since they show that we could accelerate the process of discovery by many orders of magnitude, basically from months to much less than a second once the network is trained, of course. And this was done for the first time in the literature for direct detection of substructure as a proof of principle. But of course, we knew we could get even better results by further optimizing our architecture. And so this is what we did next. We took the problem a step further and tried to cut the middleman entirely. We tried to convert the entire detection pipeline into an image segmentation task. Image segmentation involves taking an image and trying to understand what the individual components that make up this image are. And to do this, with my former postdoc here, Brian Osdiek, we used a network architecture called UNet. UNet are networks well known for their success on image segmentation, for example, in biomedical research. And so here we taught the network to reconstruct the convergence field by classifying every single pixel in the image as belonging to the background, the main lens, or one of various subhalo mass classes. The input is a strong lens image and the output is the probability for each class. So here I'm showing you the confusion matrices for 2 cases with different noise or different number of orbits in the Hubble Space Telescope. And so we see, you can see here that the network struggles to find the lower mass subhalos. And this is because the level of noise here is just above the pixel brightness changes due to the presence of these subhalos. And we provided an exact mapping in the paper that helps us understand exactly where we lose sensitivity. So we understand exactly why we are losing sensitivity here or here in this case. But we also see that the network does fairly well for subhalos above about 10 to the 9 or a few times 10 to the 9 solar masses, which are again numbers comparable to the ones cited in the literature using standard methods. Moreover, we show that the network can actually find not just one subhalo at the time as it was trained for, but in fact it can find a lot at a time. And on the left here, I'm showing you one such example. So now we can combine many of these images to measure the logarithmic slope of the subhalo mass function, which can give us insights on the nature of dark matter. And we can see here how combining more and more images, of course, reduces the error bars. And it's interesting to know that if you combine, say, 1,000 images, you can get down to 10% errors. So this is quite exciting. In fact, I think we have very exciting years ahead of us with the large number of opportunities machine learning is bringing and will continue to bring to the field. Here in the Boston area, as Ben mentioned, we started the I-5, which is a new AI institute that we started together with MIT, Tufts, and Northeastern. And there are, of course, many around the world, many institutes and many initiatives around the world. We have also recently, written white papers for the Astrodecadal survey in 2020, and we submitted another one to the SNOMAS process this week. And yeah, as I said, there are plenty of institutes and initiatives all over the world, with IAP, of course, being part of it, with many works from people like Ben Wandelt and Florent Leclerc and other colleagues. I'm just mentioning the names that come to my mind right now. So let me now switch gears and talk about the statistical approach, where we marginalize over the individual subhalo properties to obtain population characteristics. So the actual statistical observable that I will be talking about is the convergence power spectrum, where again, the convergence, remember, is just the surface mass density. So the convergence power spectrum is particularly attractive for the task that we have at hand because it provides a bridge between what we observe, strong lens images, and what we want to learn about the nature of dark matter. And the way that this is done is by the fact that the convergence power spectrum can relate length scales, which are basically deflection vectors on the lens plane, to a mass scale, which is what dark matter theories are actually predicting, the halo or the subhalo mass function. So the convergence power spectrum is a neat bridge between the two sides of this diagram. So I will start now by considering the limit in which all the perturbers are substructures that live in the lens. And once we build intuition and we understood how different microphysical properties of dark matter get imprinted on this observable, we can move on to the much more general case of a full 3D distribution of perturbers. So in a paper with Anna and Francis Yancy Racine, a former postdoc at Harvard, at my group, who is now a professor at the University of New Mexico, we developed a general formalism to study the endpoint function of the convergence field. And we started from the power spectrum. So the idea is that if we have a lot of substructure, the perturbations will look very close to Gaussian. Basically, the central limit theorem will kick in, and most of the information should be in the power spectrum. And so what we did is we modeled the convergence field as a substructure component superimposed on a smoothly varying background density profile of the host. And the convergence field of the substructure depends on the substructure position, the mass, and intrinsic properties of the subhalos that might determine the density profile. So what we did here is we proposed a change of language, moving away from talking about subhalos, and instead we proposed to talk about the correlation function of the projected density field. And the advantage of this is that now we don't need to define what we mean or we don't mean by a subhalo, as it's generally done in the literature, sometimes with different definitions. So we started from first principles. This basically has been done for the large scale structure a long time ago. And since I was more familiar with this area when I started working on this, I applied the same kind of philosophy, but for smaller scales. So basically we describe the power spectrum in terms of what we call a one subhalo term, analogous to the one halo term, which arises from ensemble averaging over the spatial distribution of a single subhalo, and a two subhalo term, analogous to the two halo term, which arises from averaging over pairs of distinct subhalos. And note here that we are taking integrals over probabilities of the mass, the intrinsic properties, and the spatial distribution within the host. So here's our power spectrum over here. I'm showing here the one subhalo term. For the remaining of the talk, I will be ignoring the two subhalo term. Ask me about it at the end if you're interested, but basically it will kick in at these very large scales. So we can see that the power spectrum is mainly described by three quantities. At low K, over here, we have a plateau, a constant amplitude. We are basically probing scales much larger than any subhalo in the system. And so at these very large scales, all the subhalos appear as essentially point masses, and the Fourier transform of that is white noise. This is what we see here. So As we move on to smaller scales, we have a turnover scale over here, given by tidal interactions of the largest subhalos in the lens galaxy. And if we could keep moving to even smaller scales to the right here, we reach an asymptotic regime where the power spectrum asymptotes to a power law. And the slope here reflects, whoops, you see my cursor, right? I hope so. So the slope here reflects the properties of the inner density profile of subhalos that you can see here, which will be different for different dark matter scenarios. So in particular, for an NFW profile used to describe the CDM scenario, this slope goes as 1/k⁴. And if we now have a non-trivial dark matter scenario, the density profile will change. Here, I took as an example over here in green, a self-interacting dark matter scenario. It has been shown that this scenario gives rise to a chord profile, as you can see in this figure. And so now we see that at small scales, we change the slope over here, which reflects, again, the fact that the subhalos inner density profile looks different in this model. The slope now goes as 1/k⁸. So here, we have a promising theoretical prediction to distinguish between different dark matter scenarios. However, of course, notice that these are very small scales, and we will probably not be able to reach them in the near future. We are talking about scales smaller than about 50 inverse, wave numbers larger than about 50 inverse kiloparsecs. But what we saw later is that by adding redshift information, we can use the information at larger scales, which are accessible by near future experiments, to distinguish between different dark matter models. And this is what I'm going to show you next. So let me now briefly discuss the redshift evolution of this observable.
Sorry, Cora. So before
yes.
before you go to this, so I understood why there is this sensitivity of the small scales on the halo profile. This is quite clear, but how could you possibly measure that? This is, yeah, I'm a bit, I missed this. How do you extract that power spectrum information from strong lensing images?
Yes. So this has been, so there are some, after this paper, there appeared the first upper bounds or the first measurements with large error bars. So there are experiments like, you can do it with HST data or with ALMA data. So basically you apply the same kind of philosophy as I did as I told you before. You divide the convergence field into a smooth component and a substructure component, and you take the residuals, and once you have the residuals, you just have the substructure component, and you can measure the power spectrum. Basically, we did that in simulations, and you can do this in the data as well. Of course, in the data it's more difficult.
But you need presumably a lot of images to get statistics that are...
Well, you can actually, I'm claiming that you can do it with one image because you expect a huge number of very low mass subhalos, right? The subhalo mass function goes as has a steep power law, goes as
Right. So yeah. So if you manage to detect those subhalos down to very low mass, using machine learning approaches, for example, yes, this is how you would get it. Okay.
Well, here actually for the power spectrum, I'm not talking about machine learning yet. We are trying not to measure the power spectrum, but we are trying the statistical approach with machine learning. It has been actually, I'm talking about an actual measurement. The statistical approach has been done with machine learning recently in a paper by Stanford people, Sebastian Wagner-Carena, Risa Weschler and company, and the paper appeared about 2 weeks ago or so.
Yeah, the constraints, well, okay, we'll talk about that later, sorry. I should leave you go on.
Yeah, no problem. Please keep asking. What I was saying that I was going to talk about, yes, I'm going to talk about the redshift evolution of the power spectrum. And so these are results coming from high resolution embodied simulations that Mark Vogelsberger, who is a colleague at MIT, provided for us. So here on the left, I'm showing the evolution as a function of redshift of the power spectrum in a CDM scenario. So as we go up here, we evolve in time, okay? And so the evolution here is quite intuitive. We see that as we evolve in time, the amplitude is increasing, and this is because we are creating more and more substructure as time goes on. On the right here, I'm showing the same thing, but for an exotic dark matter scenario, which basically includes a low mass cutoff in the initial power spectrum and dark matter self-interactions, which makes the subhalo less concentrated and thus more likely to be tidally disrupted. These are simulations that were run before by Mark Vogelsberger's team. So you can see, you can see here that the fact that the subhalos are less concentrated and more likely to be tidally disrupted is reflected in the fact that the amplitude got stalled now between redshift of 0.5 and about 0, where the increase in accretion in substructure is being compensated by the fact that a lot of substructure is destroyed now. And so there is a net transfer of power from larger to smaller scales in the power spectrum, as you can see here, in the change in the power spectrum slope compared to CDM for wave numbers greater than about 2 inverse kiloparsecs. So you can see this change in slope compared to CDM. And note that these scales, wave numbers greater than about 2 inverse kiloparsecs, are scales that are accessible by near future experiments. So I thought that I would show you a plot here that gives you an idea of the sensitivity for near future experiments. This is a plot that I took from one of Francis Jan Tebrasin's papers that shows you the scales that we will be able to probe with near future space-based and interferometric data. And you can see that we will be able to reach tens of inverse kiloparsecs in the near future. So we just saw that the convergence power spectrum, how am I doing in time? Okay, we just saw that the convergence power spectrum of subhalos within lens galaxies is a promising observable to study dark matter. However, the distances involved in strong lensing systems are vast, and we expect the relevant volume to contain line of sight halos that are not necessarily associated with the main lens. And so in recent work carried out by my group, in particular, I want to emphasize 2 of my graduate students who work very hard on this, Chan Sengul and Arthur Sang, together with collaborators at Berkeley. We developed a formalism to calculate now the effect of line of sight halos as an effective convergence power spectrum. And so now, instead of having a single lens plane at some redshift, we can have any number of lens planes. And instead of using the vanilla lens equation, we now have a recursive lens equation, which couples the angular deflections of successive lens planes. And so by assuming that the perturbation due to the line of sight halos are small, we show that they can be projected onto the main lens plane as effective subhalos with some weight. And so we tested our formalism with simulations, finding excellent agreement with our analytical predictions. But we wanted to make a general statement. So what we did is we studied how the relative contribution of line of sight halos and subhalos depend on the source and lens redshift, as well as the assumed halo and subhalo mass functions. So to understand this here, I'm fixing the halo mass function, and I'm going to vary the amplitude of the subhalo mass function, this F sub parameter over here, which is the fraction of halo mass in substructure. So here, redder colors show that line of sight halos dominate, and bluer colors show that subhalos dominate. Pretty intuitively, of course, we see that as we increase this F sub parameter, the colors go from red to blue. But now the question is, which of these 3 panels are we observing in practice? And we don't know exactly what the value of F sub is, but there are upper limits based on measurements of different systems. And we see from these values that having a substructure fraction of about 2% or more is very unlikely for the mass scales that we are considering here. It is much more likely that we are in a scenario like this one over here, meaning that the line of sight halos are dominating, as you can see from the red colors over here. And why is this important? Well, here I overlaid points that corresponds to the Bells and Slacks families of galaxy-galaxy lensing. These are 2 well-known high-quality sets of lensing images. In particular, these are sets that have been used to place constraints on dark matter. And we can see that for both sets, for a fraction of substructure that we think is more realistic, these systems are likely dominated by the halos along the line of sight as opposed to subhalos, as they were assumed to be in previous studies. And so what I want to say here is that in order to translate a measured power spectrum to a dark matter theory, it is important to understand whether the subhalos in the galaxy or the line of sight halos are the dominant contribution to the power spectrum. Otherwise, we can obtain wrong inferences about the nature of dark matter. And the fact that for typical lensing configurations, the line of sight halo contribution dominates the signal should be good news, or at least we thought it was good news, since the subhalo mass function is very hard to pin down, while in comparison, halos along the line of sight live relatively calmer lives. And so in terms of current data, we are reanalyzing systems that were previously claimed as subhalos in the literature. And our analysis indicates that it is likely that a number of them are halos, or a few of them are halos along the line of sight. I say a few of them because we analyzed a few of them. So the idea is that the deflection angle caused by the interloper form a vector field with a non-vanishing curl, which cannot be recreated by a single thin lensing plane. And so moreover, the combined convergence of an interloper, a line of sight halo, and a main lens differs from a naive sum of the two. And these differences cause slight changes in the pixel brightness near the Einstein radius, which is what we use to constrain the redshift of the perturber. And in particular, this system was claimed to be a subhalo in a Nature paper about 10 years ago. And these are results from our likelihood analysis over the parameters of the source, length, and perturber. And we find that this system is indeed more likely to be a line of sight halo, as you can see here. And so our analysis also indicates that this structure is more massive than previously claimed by more than an order of magnitude. Okay, so in the time that remains, I will now move on to talk about how we can use the larger cosmological scales to learn about the dark sector, which is something that we also do in my group, to use the large scales to learn about the dark sector. So we can attempt to learn about the dark sector of the universe at a wide range of scales using different cosmological observations. And these are just some examples of work that I carried out with my group doing so. Dark matter analysis in cosmology have the huge advantage of not relying on assumptions about the dark matter density in the neighborhood of the Earth, as opposed to direct detection searches, for example. So I will give you some examples, and then I will focus for the rest of the talk in one particular example that I'm excited about. So for example, in this work over here, we showed how 21 centimeter observations at cosmic dawn can provide a powerful handle on dark matter fluctuations at about 10 to 80 inverse megaparsecs. In red and cyan over here, you can see our forecast using different types of 21 centimeter experiments, and you can see here an example of how we will be able to use these measurements to probe different dark matter scenarios. Here's another example of the power of large cosmological scales, where we tested a general dark matter scenario known as freezing. The freezing mechanism for dark matter production is a compelling alternative to thermal freeze out, where dark matter is instead produced by some feeble interactions of standard model particles. And so in this series of works, we identified a new production channel for low dark matter mass, the decay of photons that acquire an in-medium mass. We call them plasmons. And so the plasmon decays turn out to be the dominant channel for dark matter production for sub-MeV dark matter masses. And we show that using existing CMB data from Planck, you can put constraints up to 19 keV. And in the future, we will be able to do much better with, for example, CMB stage 4 and other probes of structure formation. And this scenario necessarily implies a dark matter baryon interaction, which in fact became one of the main science drivers for the dark matter science case in CMB stage 4, which I'm sure you all know, but it's a next generation CMB experiment that has been proposed, that I'm part of, together with many other people around the globe. Moreover, this is completely complementary to planned direct detection searches, which will test down to 10 keV dark matter. So this is quite exciting, and this is an example of cosmology being complementary to direct detection searches. There are many more examples of this. So I will now focus on the program that I have been very excited about. In a series of works with my group, we proposed a way to look for new particles beyond the standard model by using CMB observations and galaxy data. And this is work that we carried out with 2 of my PhD students, Nick DePorcio and Linda Xu, who is now a postdoctoral fellow at Berkeley, and my former postdoc, Julian Munoz, who is now a fellow at the CFA. So the question that we asked is, could there be new particles that decoupled at some point in this whole thermal history of the universe between inflation and an MEV? And if these particles are light relics, which means that they decouple while relativistic, they should survive until today, just like neutrinos do. And if so, they should have an effect in the large-scale structure of the universe. So we can use cosmological observations to go after them. And so a well-known example of thermal light relics are cosmic neutrinos. Neutrinos were in thermal contact with the rest of the plasma in the very early universe, and at some point they decoupled. And we can understand their temperature of decoupling through dimensional analysis. And if you do the exercise, you can see that it is about 1 MeV. This was right before the time of electron-positron annihilation. So when this happened, the entropy went to the photons because the neutrinos were no longer coupled to the plasma. And as a result, the photons were heated up. And this is why photons and neutrinos don't have the same temperature today. And it is conventional to define a factor known as N effective as a measurement of the total energy density of relativistic neutrinos. In the standard model, this number is 3.045. Now, to give you an idea of what the numbers are for the different quantities involved, here I'm showing you a plot of the temperature of what the temperature of the relic would be today versus the temperature when it decoupled. You can see that particles with an earlier decoupling talk to more degrees of freedom at the time, and they will be colder today. Once a particle decouples, basically it stops talking to the rest of the plasma, where the standard model photons and baryons keep heating up whenever degrees of freedom disappear. That's why they're colder today. You can see this in this purple line over here. Neutrinos over here decouple before electron-positron annihilation, and the temperature today is about 1.95 Kelvin. For decoupling temperatures high enough, for which we have counted for all the degrees of freedom in the standard model, the temperature today corresponds to 0.91 Kelvin. And so if there was a relic at some point, its temperature today, in the most conservative scenario, would be from 0.91 Kelvin to 2.7 Kelvin, which is the temperature of the cosmic microwave background. And again, this is the most conservative scenario in which we have a minimal extension for a relic particle. So as a result, you can go look for any particle that decoupled at some point and parameterize it by its temperature today and its degrees of freedom. And if the relic is relativistic at all times, you can calculate the contribution to the radiation energy density through this factor N effective. And as I mentioned, for the standard model, it should be about 3. So any number that it is not 3 is telling us that there is something else other than neutrinos. And so the contribution of a relic is proportional to the number of degrees of freedom times the temperature of the relic to the 4. And this purple line corresponds to scalars. And as you make the temperature lower and lower, the N effective becomes, the delta N effective becomes smaller and smaller. Basically, it goes from order unity to 0.027 at the bottom. And in fact, this 0.027 is a target for CMB stage 4. So what's the effect of an effective on the CMB? As you change an effective, basically you change the expansion rate of the universe, which in turn affects the CMB damping tail. And it is the Hubble rate that controls the amount of diffusion that happens for photons diffusing out of the gravitational wells. This is called silk damping. And so with more an effective, the sound waves get more diffused. And therefore, by measuring the damping tail, you can get a tight constraint on an effective. And this has been done in the literature many times. Now, the best limits from Planck are from Planck and are delta and effective of about 0.2 at the 95% confidence level. So you can rule out anything that decoupled after the QCD phase transition. But there could still be new physics happening before then over here. And the hope is that CMB stage 4 will be able to bring this down at the 0.02 to 0.03 level. And this is great. But in the best case scenario, we will be able to just see a hint of it. And so something interesting that you can ask is, what happens if the relics aren't massless? And so we gave these particles the acronym LEMURs because they are light but massive relics. They are relativistic at decoupling, so they are light. They behave like matter today, and they are relics because they were in thermal contact with the standard model, just like neutrinos. And so I will tell you now about, in the last few slides that I have and the last few minutes, about the dedicated search we did for these particles. And so the idea will be that instead of looking at the 1D plot of just temperature and effective, as it has been done many times in the literature, we will expand it by looking at the mass of these lemurs. So what do lemurs do to the large scale structure of the universe? This is a cartoon to point out that the gravitational evolution is different from particles that are slow moving and particles that are fast moving. Just like in the case of neutrinos, small scale density perturbations will grow more slowly than large scale density perturbations, and the relevant physical scale of the problem is given by the typical scale a lemur, the typical distance a lemur can travel in a Hubble time. So we will have a suppression in the matter power spectrum at scale smaller than the lemur's free streaming scale, given by the ratio of the mass and the temperature. And the size of this suppression depends on the present abundance of lemurs, which is proportional to the mass times temperature cube. So if you have a relic now with a mass and a temperature, you can hope to measure both parameters using the large scale structure of the universe and not just a degenerate combination of the two. So we did a scan for lemurs using CMB data from Planck, galaxy data from BOSS, and weak lensing data from CHF-T lens, marginalizing over lambda CDM parameters, neutrino masses, as well as bias parameters. And so to go to the point, we didn't find them in the data, but our work set the current best limits on them. So anything in the color band over here is allowed, is currently allowed. So it's allowed by current data. We can see that for very low masses, we recover the ineffective bound from the CMB, delta N effective of about 0.2. And, but as you make the relic heavier and heavier, you start deviating from this bound. And so this is an improvement over an effective. And so we classify the lemurs by their spin. We can have a scalar like an axion, a vector like a dark photon, a Weyl fermion, like a gravitino or a sterile neutrino, or a Dirac fermion. And these are the limits that we found at the minimum temperature of 0.91 Kelvin. So using all these complementary data helped us to set the best limits on relics, in particular using the large scale structure data. An interesting case that we mentioned in our paper is that of the gravitinos. Using our limits, we can say that the gravitino mass has to be below 2.3 electron volts. And this is about a factor of 2 stronger than what we had in the with the CMB before, and almost an order of magnitude better than what we had with the Lyman alpha forest about 15 years ago. And this can be translated, this bound on the mass of the gravitino, this can be translated into an upper limit on the SUSY breaking scale for this type of models, which now has to be less than 70 TeV, which is strongly complementary with lower bounds from colliders. Okay, so I will end my talk here with a few concluding thoughts. So I divided my talk in terms of scales. I started with the smaller scales and I focused on a purely gravitational technique. I showed you how we can use gravitational lensing to probe dark matter at kiloparsec scales, which is a regime which so far has remained much less tested. I told you about ways to enhance direct detection with machine learning techniques. And I also talked about the statistical probe, the convergence power spectrum, which has the advantage that is sensitive to lower masses than direct detection. And it provides a more direct link to dark matter theories. And finally, I showed you also how we think that the line of sight halos are likely the dominant contribution for typical galaxy-galaxy lenses, and that I think this should be good news for our ability to draw conclusions about the nature of dark matter in an unbiased fashion. For the larger scales, we focused on the search for lemurs, light but massive relic particles. The search for lemurs complements current efforts on an effective, opening a new route for finding physics beyond the standard model. And this past week, we put out a SNOMAS white paper together with Joel Myers, where we make this point. We set the best limits up to date with current data, especially with the help of the large scale structure. And finally, looking at the future, it is very possible that the first relic detected will be massive, since this is the first kind of relic we should be able to see. In fact, we expect to see a very large improvement in the sensitivity to lemurs with upcoming experiments like DESI or Euclid and CMB stage 4, in some cases covering the full parameter space. And more generally, I want you to leave with this take-home message, which is that this decade is bringing a wealth of new and complementary data sets, and we will continue to exploit their complementarity and look for new ways to shed light on the dark sector. So stay tuned. Thank you.
Thank you very much, Cora. You have to imagine us applauding you enthusiastically.
I had 2 years of experience on that.
There was a question on the chat that, that I'll read out, and maybe you can comment, from Julien Laval. Are you, this is for the subhalo, you're looking for subhalos to constrain dark matter. Are you assuming a subhalo mass threshold when you define the fraction of subhalos?
Right.
Because
yes, I am.
You can't probe that fraction down to arbitrarily small masses. So,
right.
And how do you choose that?
Yeah, so we were working for our simulations and our analytical predictions. We were assuming a minimum mass of 10 to the 5 solar masses, going up to, I think in this paper, we assume going up to 10 to the 8 solar masses, because the idea was that above 10 to the 8, this should be detectable. Probably 10 to the 9, but anyway, I think the range was 10 to the 5 to 10 to the 8. So that's why this F subparameter depends on the range of masses that you are assuming. No? So in this case, I talked about 0.54%, but that's for our mass range.
Good. Are there any other questions?
I see Florian.
Can you hear me? Hi.
Yes, hi.
Hi, Cora. Thank you very much for the talk. That was very interesting. I have a cosmological question and maybe a more technical question. So, well, I guess I'll start with the cosmological question. That was on the search for light relics.
Yes.
You had this contour plot with different nature of particles, scalar, vector, Weyl, Dirac, and yes, it seems that there is no effect on sigma 8 from the different nature of the particle, but there's an effect on mx. Could you maybe explain where that comes from?
Oh, no. So there is so the main degeneracy that we see is between the lemur mass, MX, and the omega cold dark matter sigma 8 combination. And so to keep the matter density fixed, the effect of a larger lemur mass can be partially compensated by reducing omega cold dark matter. So this results in an overall smaller amount of clustering matter, and so consequently a lower observed value of sigma 8. But we are imposing CHFT lens, so we are using weak lensing measurements to put a bound on sigma 8.
I see.
Yeah, yeah.
Can I ask a second question then?
Go for it.
Sure, thanks. So that was on small scale, on gravitational lensing at small scales and these U-nets.
Yes.
One thing we are faced with when we try to fit full images with, not with neural networks, but with Bayesian techniques is typically these issues of model misspecification, where we can never specify a model which actually fits the data. So I was wondering if there's something, how you can handle this issue of model misspecification when you're using these units.
Yeah, actually, so thank you for asking this. We are changing the way, so I presented this, but we are changing the way now we are working on this problem, because so the main source of confusion here is, and the decrease in accuracy is coming from the source complexity. And you're right, like how can you do a general, how can you account for any type of source that you see? So now we are changing, and so here it was an example. We took examples of sources with a few sources modeled by a few sources with some clamps, but sources can be very different. So now we changed the way, this is work in progress in which we are doing this, and we are basically more targeted to actual observations, right? So the way in which we are doing this is we are first going to characterize the source, not with machine learning, just directly characterize the source. And then so it will be a targeted thing. And then we will use machine learning for seeing whether there are subhalos or not. But it's, as far as I can tell you, everything that we tried to model actual sources didn't work. So it's really hard to do this generically.
Thanks.
Any other questions?
Yeah, thank you. Those are both great questions.
So I have an easier question than Flo. How do you deal with the uncertainty estimation for these estimates? Right, the units are trained to give you a best estimate.
The units are trained to give us a best estimate. So we have the probability, right, in each pixel. That's all we have, really. You mean the uncertainty and the probability?
Right. Mm-hmm.
Yeah, we don't have that.
Mm-hmm. Right.
That's a good question.
So you're computing you're interpreting the output of the network as a probability, but then of course you rely on training working and the network being expressive enough, et cetera, to have a good estimate.
Yes. And we actually are moving away from units as well. I'm showing, we are learning in the process. So, units are great, but as you say, there are a few things that are a little bit more difficult in this case.
Right, that's a general problem, right? How to do uncertainty estimation in these contexts. I noticed that you're collaborating with the Montreal group, and so they've become very interested in techniques where you derive the uncertainties from estimating posterior densities rather than sort of doing point estimates. Right?
Yes.
Estimation, accurate free inference.
Yeah, actually, the Montreal group, you said?
Yeah.
Yeah, I would like to collaborate with. We have not collaborated yet with the Montreal group, but this is a very nice approach.
Yashar Hezeve is there. I noticed him on some of your papers. So.
Yes, in the white paper. Yes.
I see.
But yes, you're right. These are great techniques.
Any other questions? This stage. If not, then let's thank Cora again for the way to